Okay, chapter 2 is we're going to talk here about water. And water is a pretty cool little molecule. It absolutely makes life possible. When astronomers look out into outer space and they look at planets and moons and other things, one thing they are looking for is water. And if they find liquid water, they get very excited. And the reason they get so excited is that with liquid water, there's a good chance that life could or is living there. So it's a key thing for life. One reason water is so cool is because it has something called covalent bonding or polar covalent bond, which means that water shares its electrons unequally. Oxygen here you can see is slightly negative. It pulls the electrons towards it and therefore takes a slight negative charge, and the hydrogen there takes a slight positive charge as the electrons get pulled away from it. This causes water to act like little magnets where these little positives and little negatives will kind of stick to each other a little bit. And that's what we call polar, where we have the slight positive and slight negative charge from unequal sharing. What this unequal sharing does is it allows water to form something called hydrogen bonds. Now, hydrogen bonds are bonds between water molecules. They are not in the water molecule. You have to have several water molecules, and they will slightly bond to each other. Those slight positives and slight negatives will bond to each other just very briefly for less than a millisecond, and then they will release and bond to another water molecule, and this will go on in the water. You can see here in this picture that the slight negative, this is a picture of your hydrogen bonds, the slight negative of oxygen bonds briefly to the hydrogen, which is slightly positive. And again, so you can see this is bonds between molecules. It's not inside one molecule. It's molecules bonding to each other. And they slide past each other in liquid water and then will bond to the next one and then to the next one. So the sum total of hydrogen bonding allows water to kind of stick to itself and kind of stick to other things. But each individual hydrogen bond is very, very weak. What makes it strong is that they're all doing this over and over and over again. These hydrogen bonds give water its life-supporting properties. So, and when we talk about life-supporting properties, we're going to talk about cohesion, which you can think of a cohesive group of people where they kind of stick together, where water kind of sticks together. You can think of adhesion, like an adhesive tape, where it sticks to something else. And there's also something called surface tension, and that's caused by the cohesive nature on the surface of water sticking together. And you can see that when a glass overflows a little bit. You kind of get a bubble on the top of the glass before it completely overflows. That's the surface tension. Now, this hydrogen bonding is also used in trees. And you can see in this tree here that the hydrogen, well, what's happening is the water is taken up in the roots, we know that, and it's going to go to the leaves and transpire. Well, how does it get pulled up the middle of a very tall tree? And the answer is it sticks to itself. So even as you suck up a straw, you can imagine the water kind of sticks to itself. Imagine all these kind of tiny, slightly magnetic things holding on to each other, and they will also hold on to the surface of the straw that you are sucking up. And that's the adhesive property, and that is how you can get water to go up a tree. If you end up with an air bubble in there, it actually won't work. You need a continuous flow of water for the cohesive property to get it up there. Okay, here's a nice picture of surface tension, and you can see, you can actually, if you look at the water carefully, you can see some dimpling in the water, and that's the surface tension. The bug obviously has not broken the surface tension, and that's how they, you know, quote unquote, walk on water, is by using the surface tension of water. Okay, another cool thing about water is that the hydrogen bonds moderate temperature. And what this means is if you go to San Francisco, it's very rarely super, super hot or super, super cold. And that is because water can literally absorb a lot of heat energy, and then as things cool off, it can release that heat energy back into the city and kind of moderate it. Well, animals use this. We use it. We're mostly water, right? So we're mostly made of water. So we use that ability for the heat, for water to slowly heat up and then to release that energy back. Okay, it takes a lot of energy to disrupt hydrogen bonds. Now, remember I said they're pretty weak bonds, but they're happening all over the place in the water. There's tons and tons of them. Each water molecule is hydrogen bonded to its neighbor, so you have lots of them. And you have to break these hydrogen bonds to get the water moving, which is what temperature is. It's molecules moving faster. And so that's where the energy goes. When we talk about water can take a lot of energy to heat it up, well, the energy goes somewhere. It goes into breaking those hydrogen bonds. Then again, as it cools, where's the energy come from? It's from the formation of these hydrogen bonds, right? We've broken them. Now they're going to reform as the molecules slow down. Another cool thing about water is when it evaporates, it will take that energy with it. All liquids will, but water can take more energy with it because it takes more energy to have it evaporate. So humans use that. We sweat, dogs pant. You can use that as a cooling mechanism, and you know you can feel that when you're sweating and a breeze hits you, it cools you down quickly. What is happening is those water molecules evaporating off your skin take that heat energy with it. Okay, another cool property of water is that it is in the solid form, called ice, is less dense than the liquid form. Now that's not true for most substances. Most things, when they're solid, are actually more dense. They would sink. You'd have ice cubes that sink. We're used to seeing ice cubes float, and so we're just used to this property, but without it, life could not exist. So you can see what happens is the hydrogen bonds on your right is the liquid water, and they're sliding past each other and reforming and reforming and reforming. And as we slow the molecules down on the left side, you see the molecules line up, and they stop sliding past each other, and they kind of push each other apart at that point. What this does is it makes ice less dense than water, okay? And that is huge for life, because if ice sank and you had a lake freeze, what would happen is it would freeze from the bottom up, and all the fish in it would die. This allows the ice to form on the top, and believe it or not, ice is a really good insulator. You can use it in igloos, and it will actually trap heat. Well, what that does on the lake is as it's freezing, the ice on the top protects the rest of the water from freezing, allowing the fish to continue living underneath that frozen ice. And again, when we look in the solar system, sometimes we hope there's liquid water under the ice. All right, when we talk about water, the cool thing is that it can be a really good solvent, and sometimes it's called a universal solvent for life, but it's not really universal. It just happens to be really good. And a solvent is the liquid that something is dissolved in. The solute is what we have dissolved. This beaker is just a classic example of salt water. Table salt is sodium chloride, and that is your solute, and the solvent in this case is water. Again, it's a very good solvent, which makes it great for life. All right, so you can see why it's such a good solvent. If you look at the sodium and chloride in the picture, and you look carefully, the sodium, which is a positive ion, it's the one Na there in yellow, all the oxygen, and if you remember, oxygen is negatively charged or has a partial negative charge to it, line up around and surround the sodium. And then on the chloride side, you can see the Cl, which is slightly negative. It's the larger green one. it gets surrounded by the slightly positive hydrogens. And that's what makes it such a good solvent, is that these molecules can kind of line up and surround these solutes. Okay, water disassociates, and it disassociates at a very small rate. It's 10 to the negative 14th or something like that. It is not much, but it's very important because as you get hydrogen ions in water, which is what occurs when it disassociates, you get something called acids and bases. And life can use acids and bases to make energy and to do all kinds of things. So it becomes, even though it's a small amount, the effect can be quite large from this disassociation. And we can measure that. We use a pH scale to measure that. You can see lemon juice is about 2, Diet Coke is somewhere 3, so I'm sure it's not good for my teeth. Water is very neutral, which is a 7, is pure water. And under the neutral, you can see the disassociation, the hydrogen, and then the OH is the hydroxide ion of a disassociated water. The more hydrogen ions you have, the more acidic it is. 1, 2, 3, 4, 5, 6. The more hydroxide ions you have, the less hydrogen ions, the more basic it is. 8, 9, 10, 11, 12, 13, 14. Some bases can be quite strong. Ammonia, bleach, very, very powerful bases. And then obviously some acids can be quite strong as well. Most cells like to keep a pH of about 7. And one way they do this is something called a buffer, a pH buffer. And it can release hydrogen ions or absorb them back in depending on the pH. And that can help moderate the pH in the cells, which is important because our cells don't like to get too acidic or too basic. Okay, acid precipitation, also called acid rain, is pretty important, not so much on the West Coast, but it's huge on the East Coast. It is caused from burning fossil fuels. They release a sulfur into the air, and you get sulfuric acids. You can also get nitric acids into the atmosphere, and then it rains down, and it can kill trees and get into the water. Again, not too much on the West Coast, but East Coast and Europe has a big problem with it. You can see the acid rain here killed the trees. Maple trees, where you get your maple syrup from, if you get the real maple syrup, are very susceptible to acid rain. And limestone, which a lot of churches in Europe and some on the East Coast, but a lot in Europe were made from limestone. And on the right here, you can see a picture of the same statue. The one on the left here was taken in 1906. I believe the picture on the right was taken in 1968. So you can see that in 60 years, there was enough acid rain to significantly damage that limestone. You can't see her face anymore. It's kind of all dissolved away. That's from the acid rain dissolving the limestone. Okay, chemical reactions occur in our bodies all the time. All day long they're occurring. They occur very quickly. And so a chemical reaction, this is a chemical reaction of taking hydrogen and oxygen and creating water. On your left are called reactants. Those are the things that are going to react. And on your right, we call those products. That is what we have created at the end of the reaction. So you have reactants on the left here. You have your product on the right. The product in this case is plain old water. Living cells, again, they do reactions all day long, and they do it very quickly. They make vitamins in this case, but they make proteins, they make carbohydrates, starches, sugars, and they also use those sugars for energy. So they both make and create things all day long. So reactions are very important when we talk about living things. Okay, this is a very common reaction in biology called photosynthesis. I'm sure many of you know this is my favorite reaction because you take carbon dioxide and water, add some light energy, and you get sugar out of it and oxygen. What could possibly be better, except for maybe caffeine, but in this case it's sugar. So you take carbon dioxide and water, those would be your reactants. And then your products in this case would be glucose and oxygen. Okay, so the reactants in this one were, like I said, carbon dioxide and water. the products, glucose and oxygen. All right, if worldwide, if you had the oxygen productivity go up, the question here is, what would you expect carbon dioxide levels to do? Would they go up, would they go down, or would they remain constant? So this equation, we are using up carbon dioxide with water to create glucose. So the answer is, if we do more photosynthesis, carbon dioxide would actually go down. Now the flip side of that, remember carbon dioxide is a greenhouse gas, is that with less photosynthesis, carbon dioxide will go up. All right, so like I said, carbon dioxide goes down with increased productivity.